start this lecture 12 with a thought process from Max Planck. It goes like this: anybody who has been seriously engaged in scientific work of any kind realizes that over the entrance to the gates of the temple of science are written the words, that is, you must have faith, and that is true for the life. If you want to do a carry out a decent life, you should have faith in yourself, and faith in yourself cannot be achieved unless you have faith in relationship, faith in the heritage. So, therefore, it is very important to look at the holistic approach to the life. So, that also Max Planck has talked about the science. So, let us recall what we learnt in the last lecture. We basically use the isentropic analysis to discuss about the processes involved in a nozzle. We discuss about basically two nozzle, one is conversion nozzle, other is diversion nozzle, and then I introduce a concept known as choked condition or the choked flow. Now, we also invoke the mass flow rate expression or mass flux expression and figure it out how this choke flow can be avoided in real situation. I had asked one question, that whether we can use this choked flow as it is disadvantages all the times for our advantages. Is there anybody who really mulled over it? Let me give you a clue, that when you are designing an experimental setup, can you use this concept to your advantage? Because unless otherwise you get your answer to the question of yours, of course, then you cannot get faith in yourself. So, it is very important to think about it and get the answer. So, let us now look at what do we mean by a shock. What do we mean? We do all experience shock in our life. For example, I was traveling maybe a month back in my cycle on the road, and suddenly a motorbike bumped into me. I couldn't really do anything, right. So, because why I couldn't do anything? It came suddenly such that my mind was freezed. I couldn't really do anything to have any action on it. So, that is one kind of shock what we experience. Any sudden things which will give a shock, that means what is the meaning? It will be giving a kind of a freezing or kind of coming to an end, you cannot take any action. Similarly, what happens in the fluid, that when the fluid is flowing, right, you suddenly ask to stop. What will happen? I will give another example to appreciate what do we mean by a shock. In the highway, all the cars are moving at a very terrific speed, right, maybe 100 km per hour. All of a sudden, a policeman says that stop, right, by using hand. What will happen to the cars which are moving at a terrific speed? What will happen? They will come, let us say at this place the policeman is there, but the far away from the this what you call policeman signal, nobody can see that he has asked to stop. So, then what will happen? Car will be coming here, and at a certain distance it will be stopping or trying to stop. As a result, they will be colliding, coalesces, and of course, after that they will again move. What? Of course, they may be some roughened out, and they may move at a slower velocity. if they can manage to. So, that means what is happening? It is a shock is being formed. Of course, this thing you need to imagine and then have a feel. Question arises in this example, why it is happening, and enough time to stop. That means, the signal given by the policeman or the traffic policeman can't be really followed by that, already they have come in. So, that means, they are getting compressed nearby to the police post, right. Suppose this is a police post nearby, they will be trying to get compressed, right. Let us look at whether similar thing is happening here in an aircraft which is moving, right. This aircraft, let us say it is moving and air is still, right. That means, air is moving, the aircraft is moving, right, okay, for the time being, then air is moving. What is happening then? It is like a piston which is moving the fluid towards the left, towards the this side. That means, if you recall that I had taken a piston cylinder examples, like when we are discussing about the speed of sound. That means, this is creating a disturbance because of movement of the of an aircraft in the steel fluid, and that disturbances travels. At what speed it will be traveling? That will be speed of sound, right. Now, that means, it is a disturbance created by the presence of an aircraft or any other body, right. It is now imagine that my aircraft is stationary and fluid is moving at a very, very high speed, right, and my aircraft is stationary, which can happen in a wind tunnel kind of things, right. So, then if the flow is subsonic, then what will happen? Because if the flow inlet fluid here, it is moving towards the aircraft at a subsonic speed, then what will happen? Because the signal from the what you call this aircraft can reach the fluid element, and fluid element will take care of it, and such that it will be just gliding over the surface, such that it will be going. But if the velocity here is quite high, if it is v infinity is greater than the speed of sound, then what happens? It will be coming straight, right. For example, if I take this, it will be coming straight, right, and then it will be knowing that by certain distance, like that of course, depends upon several conditions, like that there is a what you call an aircraft, such that then it will be coalesces in this region, right. So, for this streamline is concerned, then after that it will be going at a slow down and then travel, right. Travel what? Whether it will be subsonic, whether it will be supersonic, right. How it will happen, all those things we will be looking at it. But if you look at as a result, there is a thin region here, right, which occurs, and that region is, you can call it as a wave. Basically, it is a compression wave. Keep in mind that in this case it will be stationary, right. And if you look at this region, in this region, just in the stagnation point over here, I can say that it is perpendicular to the velocity, right, this region. Then that we call it as a normal shock, right. That means, a compression wave perpendicular to the supersonic flow, then we call it as a compression. Keep in mind that this is not really perpendicular, except at the stagnation point or the line along the stagnation point, it is little bit curved, but we are assuming it to be a normal for simplification. However, in this region it is a oblique shock because it is making an angle to the incoming fluid, right. Therefore, it is we call it as a oblique shock, and in this region we call it as a Mach wave. What is that Mach wave? Can anybody tell me? That means, when the speed velocity or velocity fluid velocity is closer to speed of sound, then there will be a compression wave, but which is intensity of it will be quite less. That is known as Mach wave. We will be invoking this concept little later on. And if you look at what will be the thickness of these waves, what will be order of, can anybody guess? 10 power to 5 what? 10 power to minus 5 meter, is it so? Meter is really big or small? Actually, it is 10 power to minus 5 centimeter. In other words, it is 10 power to minus 7 mm. In other words, it is 0.1 micron. It is a very, very thin region, right. And let us look at where else we will be encountering, so far propulsive device is concerned, the normal shock. That if you look at, like when an air intake, basically supersonic air intake is being used, there is a likelihood of that a shock will be formed near this cowl leaf, right, and it may be touching or it may be away. Of course, those things which we may discuss sometime, right, and there is a normal shock which we can think of. But keep in mind that what I have shown here need not to be formed in real situation, particularly in this region, it will be different, right. Okay. And if it is so, if it is away from that, it may be a bow shock, like this is a bow shock known as, okay. It is like a bow, arrow and bow. So, but however, we can approximate it as a normal shock, and beside this there is another place where we will be encountering normal shock is the in a CD nozzle. CD means convergent divergent nozzle. You remember I was talking about it yesterday, right, and what I have shown here is the divergent portion of CD nozzle, right, and convergent portion is there in the upstream, which is not being shown in this diagram. Of course, there will be a throat, convergent portion, then throat, then divergent portion, which I have shown here. Under what condition a normal shock will be formed? It is not only the choked, but also when the pressure, back pressure will be above the design pressure, right, then only a normal shock is likely to be formed, depending on the how far this back pressure is higher than the design pressure for which this convergent divergent nozzle is designed is being the location of this shock will be dependent on that, right. Keep in mind that in real situation this shock won't be what I have shown here like a normal shock, because boundary layer will be there. When boundary layer is there, the fluid will be what? Subsonic, right. And similarly, in this region it will be quite complex in nature, right, which I am not going to discuss now, maybe later on we will see. But in the major portion, because in the accelerating flow the thickness of boundary layer is very small. So, therefore, in major region one can consider to be normal shock, right. So, now what we will do? We will be trying to analyze this normal shock and see how we can predict the properties across the normal shock, right. So, let us do that, and keep in mind that these properties, right, will be changing across a normal shock, and there will be irreversible discontinuities in the properties across a normal shock, right. That means, the processes will be irreversible in nature, but then how we will do it? Because what we have discussed now is only for isentropic flow, not for non-isentropic flow, right. As I told that we will be using all the time isentropic flow relations for analyzing our what you call propulsive devices and the phenomena like shock formations and other things, right. So, let us look at normal shock, which is occurring over here in this region. Keep in mind that this is a fixed what you call normal shock, and in which the fluid is coming over here at a certain velocity v 1, right, and it is leaving the normal shock at certain fluid properties like rho 2, P 2, V 2 and T 2, and in the inlet to this normal shock, that is rho 1, P 1, V 1, T 1. Keep in mind that both are different, and in this case we are taking that A 1 is equal to A 2, because it is a constant area kind of things we are considering, and we will include this normal shock and take this dashed line as a CV, control volume, right. That means, my control volume will be like this. Now, we will make certain assumptions, which we have already done. Just for the completeness sake, I will enumerate them. That is, we will be considering it to be a steady one dimensional inviscid fluid. That means, there is no dissipation effects, right. Okay. That means, there will not be any friction effects in this case, and dissipation, of course, there can be different kinds, right. It can be mass diffusion, it can be like thermal diffusions and other things, and there is no heat is going out of this control volume. You are not really heating it, right, or nor any combustion is taking place, nor you are cooling it. So, we can assume to be adiabatic. Of course, the fluid will be at a higher velocity, right, and then naturally we need not to worry about gravity, and there is no work done here. So, no shaft work, and keep in mind that shock is thin, right. As I mentioned just now, I mean that the thickness of the what to call shock will be around 10 power t minus 7 mm, right. So, it is a quite a thin, and we are using ideal gas equation with a constant property, thermodynamic properties. That means, it is basically what calorifically perfect gas we will be using, and we will be now considering what to call rather invoking all conservation laws like conservation of mass, that is continuity equation, and if I take this control volume and also the steady flow condition, this will be 0, and then for this control volume what it would be? It will be between station 1 and station 2, it will be rho 1 V 1 A 1 is equal to rho 2 V 2 A 2. As A 1 is equal to A 2, then rho 1 V 1 is equal to rho 2 V 2, which we have already seen, right. So, we need not to spend much time on it. Let us look at momentum equation, that is steady process. So, this will be 0, and then we will have a what you call the surface, that means, we are not considering the friction forces. So, therefore, we need not worry about it, no gravitational or the body forces rather, will be 0. So, this turns out to be what? If you look at this term convective sum, that will be turning out to be rho V 1 square, right, or rho V 2 square minus rho V 1. This term if I write down, I can write down rho 2 V 2 square A 2 minus rho 1 V 1 square A 2 is equal to minus P 2 minus P 1. Can I not write like this? Because this term, this is for this term is for this left hand side and this term is for right hand side. So, when I simplify it, I will get basically P 1 plus rho 1 V 1 square is equal to rho 2 plus P 2 V 2 square, right. And because A 1 A 2 will be basically what you call cancel it out kind of thing. So, we may not consider A 1 A 2 kind of thing. So, and keep in mind that A will be there here, right, and this will be what you call this A 1 is equal to A 2 is equal to A. So, therefore, it cancel it out, right. And if you look at this energy equation, and similarly we can do this will be 0 steady flow process, there is no what you call body force gravitational, no heat losses, this will be 0, shaft work this will be 0, there is no body forces, so there will be 0. So, that turns out to be something like which we are very familiar, H 1 plus V 1 square divided by 2 is equal to S 2 plus V 2 square divided by 2. And if you look at this term is, what is this term? This term is nothing but your total enthalpy. That means, total enthalpy in the station 1 is equal to total enthalpy in the station 2. That means, what? The total enthalpy remains constant across a sock, right. And for an ideal gas, the equation of state becomes P is equal to rho R T, that we know very well. So, let us first express the property ratio in terms of Mach number, right, because we have seen this equation 1, 2, 3, 4, 5, right. Okay. So, and this equation we will be expressing now using this equation we will be expressing property ratio across a sock in terms of Mach number. So, what we will do then? Then we will find out this is T 2 divided by T 1 is equal to T 2 divided by T T 2 into T T 2 divided by T 1. Can I not write like this? Right, into T T 1 divided by T 1, right. And similarly, we can write down T 1 T T 2 into T T 1 by T 1. And keep in mind that what is saying that this is a basically station 1. If you look at, I can take this as a station 2, station 1, and then we can assume that S T 1 is equal to S T 2, right, that already we have seen by invoking equation 4. And if we take this calorifically perfect gas, or we can say that property is not changing, then I can write out T T 1 is equal to T T 2, right. So, then by doing this thing, we can really get this expression as I told. And now, what is this expression? How can I express this in terms of Mach number? I can express this in terms of Mach number of M 2 by using isentropic relationship, but I have already told that this is an what you call not isentropic, right, or irreversible processes occur across the sock. Then how can you use this? There is something wrong, am I right? Is it really wrong? Because there might be a dissipation across the sock or irreversibility across the sock, but however, so far the station 2 is concerned or station 1 is concerned, right, it will be isentropic. So, therefore, we can relate that if I will do that, we know that T T 2 divided by T 2 will be what? 1 plus gamma minus 1 divided by 2 m 2 square. I can write down here, and similarly, I can write down 1 plus gamma minus 1 divided by 2 m 1 square. So, what I am doing? I am just trying to relate these properties as station 2 and station 1 in terms of Mach number. In one case it is Mach number 1 and Mach number 2, right. So, if I know Mach number 1 and Mach number 2, I can find out very easily the temperature ratio for across a sock, although the sock is irreversible process. The processes inside the sock will be irreversible in nature, but however, I am using isentropic relation, that is the beauty of it. So, similarly, we will try to look at this, express the properties across the sock, that is P 2 by P 1, V 2 by V 1, rho 2 by rho 1, all those things we will do. So, let us find out expression for velocity ratio across a normal sock as given below, right. How we will do that? We know V 2 by V 1 is equal to what? I need to express in terms of Mach number. So, naturally, I will have to express in terms of what? Mach number. Naturally, I need to relate those things to the speed of sound and also the Mach number by the from the basic definition, that is V 2 by V 1 is equal to m 2 a 2, right, by definition, and V 1 is nothing but m 1 a 1, and where a 2 or a 1, that is the speed of sound, will be nothing but equal to, that is root over gamma r t 2, that is a 2. Okay. Similarly, for a 1, and if you look at, I can cancel this term, this gamma r. So, then that comes to be m 2 divided by T 2 by T 1, and I have already derived the expression for T 2 by T 1, that is equation 6. So, if I just put this equation in the 7, I will get V 2 divided by V 1 is equal to m 2 divided by m 1, and this term, which is already power to the half, right. So, in the similar way, I can get a expression for density ratio. Of course, for that we need to invoke the equation of what? Continuity or continuity equation, that is rho 1 V 1 is equal to rho 2 V 2. So, then I can write down rho 2 by rho 1 is equal to V 1 by V 2, right, and V 1 by V 2 I can get from this equation and rewrite that, right. And if you look at this, is just opposite of that. Equation 9 is just opposite of equation 8. So, using equation 2 and ideal gas law, we can have what you call the momentum equation in this format. What we are doing? We are basically writing, instead of density, what I am writing is here, this was rho 1, instead of rho 1, I am writing P 1 by R T, and P I have taken out of it. That means, what I am writing is rho 1 is equal to P 1 by R T 1, right. So, earlier expression was P 1 plus rho 1 V 1 square is equal to rho 2 plus P 2 plus rho 2 V 2 square. So, in place of rho 1, I am putting it P 1 R 1 T and taking it back. So, I am getting this expression, right. If you know that this V square is nothing but m square gamma R T, right. So, if I write down this equation, what it would be? This will be P 1 1 plus m square gamma R T divided by R T 1 T 1. So, this will cancel it out, is equal to P 2 1 plus m square gamma R T 2 divided by R T 2. That means, what I am getting here? I am getting P 1 plus gamma m 1 square and is equal to P 2 plus gamma m 2 square, right. And I can rewrite this expression as P 2 by P 1 is equal to 1 plus gamma m 1 square divided by 1 plus gamma m 2 square, right. This is the pressure ratio relationship between Mach number and gamma. So, similar way, by using this equation 5 and equation 6, we can find the relationship between m 1 and m 2, because what we have done, we have really basically express all the ratios like P 2 P 1, rho 2 rho 1, T 2 T 1, m in terms of inlet Mach number, that is m 1 and m 2. But I may be knowing the m 1, but do you really know the m 2? If I do not know, then naturally I cannot really use this expression, these expressions will be useless, right, yes or no. For example, if I know this m 1, I cannot evaluate P 2 by P 1, although I know gamma, let us say for air it is 1.4, but I need to m 2. That means, I need to find out a relationship between m 1 and m 2. If I know that, then I can substitute express this P 2 by P 1 in terms of m 1, right, inlet Mach number, then I can do that, right. For that, what we will do? We will be invoking this equation 5 and 6 to find a relationship between m 1 and m 2. This is quite important, right. So, what we will do? We have already seen that T 2 by T 1 is nothing by P 2 by P 1 rho 1 by rho 2, and P 2 by P 1 will be nothing but this portion, that is 1 plus gamma m 1 square divided by 1 plus gamma m 2 square, which I have shown here, right, in this region, and rho 1 rho 2 you can use that expression and then put this equation here, like this is for the rho 1 by rho 2. And but already we know that T 2 is equal to 1 plus gamma minus 1 divided by 2 m 1 square divided by 1 plus gamma minus 1 2 m 2 square. That means, this T 2 expression must be same as that, am I right? Yes or no? So, that means, I can write down this portion is same as that. If I cancel it out this, right, because if you look at this term is same as that. If I cancel it out that, what I will get? I will get half over here, yes or no? Because this I am cancelling out, this is not there. If I divide it, this portion if I take and divide it here, it will be half, right, 1 half, the square root. So, if I will then square this portion, that means, I am squaring here, also this squaring here, and if I do square, this is cancel it out, then I will get an expression, right, that is 1 plus gamma minus 1 divided by 2 gamma m 1 square. This is the portion, because I cancel it out, I am taking this portion, this portion over here in this place is equal to m 2 square divided by m 1 square, this portion, right, this portion I am taking over here, and then this portion I am taking square. If you look at this portion, I am taking to this, right. And if you simplify these expressions and also the solve this equation, you will get an expression like this, that is m 2 square is equal to m 1 square plus 2 divided by gamma minus 1 is divided by 2 gamma power divided by gamma minus 1 m 1 square minus 1. Keep in mind that this is a first solution for whatever the equation we have seen, right. Now, if you look at this equation 11, we have gone through a very arduous path of doing that, but it can be used, it can be derived very easily by using the concept of specialize what you call energy equations, and then you will reach a Prandtl relationship, right. That means, all these equation you need to, all these points we need to go to the characteristics point or the characteristics Mach number, which I am not doing, but I will give an assignment to look at it, right. Because this is little arduous, but I thought I will do that, and that is a very simpler part which you people will need to look at it, because those concepts will be using, right, in our what you call later on while solving certain problems, which is easier. So, what it indicates here? It indicates that m2 is a function of m1 and gamma, right. It is saying that m2 is a function of m for a particular a, that means m1 will be controlling what will be the m2. For example, if I say that m1 is equal to 1, that means what? The velocity is equal to speed of sound. If m1 or the what you call free stream velocity, in this case if it is shock, right, is equal to the speed of sound, then m2 will be, if you put this one, what will be? If I substitute this equal to 1, m1 square is 1, what will be turns out to be? This to be, this portion will be equal to 1, and when m1 is equal to 1, then m2 also equal to 1, right. That means, that is known as a normal shock wave, which is, I mean basically normal shock wave we are looking at, and this is vanishingly very very small. So, therefore, it is known as Mach wave, right. Its strength will be very very small. Now, if m1 is greater than 1, what happens? If you look at this term, what will happen? You will see that m2 will be less than 1. If m1 is greater than 1, if m1 is greater than 1, m2 will be less than 1. That means, if the supersonic, the upstream fluid is supersonic, the downstream of the shock will be always subsonic, right. But if m1 is tending towards infinity, that means it is very high, let us say 40, 30 Mach number, right, I mean very very high, then what will happen to the m2? It can be 0, is it so? It will go to a certain values. When you take de Hospital rule, apply to the equation 12, you will get a relation that is root over gamma minus 1 divided by 2 gamma. If I take gamma is equal to 1.4, under this condition, what will be m2? That means, when Mach number tending towards, this will be something 0.378. Beyond this, you cannot really go, kind of things. So, it will be going towards that value, right, when it is very very high. So, therefore, it cannot, one can think of, oh, it is vanishingly small. If if it is 1000 Mach number, then it will be 1 over that. It is not that way. Okay, it is not that small. So, it will be going to a value which is beyond that we cannot. So, let us derive an expression for total pressure ratio across a normal shock, which is very important. PT2 divided by PT1, right, is equal to, we will be using similar relationship even in the cycle analysis here. You keep in mind, I can rewrite PT2 divided by P2 into PT2, P2 divided by P1 into P1 divided by PT1, right. And then I can put this expression, all those things, I can get this, right, equations very easily, right. And now, what we will do? We will put here the expression for m2 in this place, right, and because for to evaluate this PT2 by PT1, we need to evaluate this P2 by P1, right. So, what we will do? We know P2 by P1 is equal to 1 plus gamma m1 square divided by 1 plus gamma m2 square. So, in place of m2, I will put this expression 12, and I will get this expression. If you simplify it, right, you will get an expression P2 divided by P1 is equal to 2 gamma divided by gamma plus 1 m1 square minus gamma minus 1 divided by gamma plus 1. And if you simplify further, you will get, you can take it out to gamma divided by gamma plus 1 into m 1 square minus 1 plus 1. And this little algebra you can do, I will leave as it is. And what it indicates? It indicates that P 2 by P 1 is function of inlet Mach number, that is m 1 and gamma, right. So, if you look at m 1 is equal to 1, what happens? P 2 by P 1 will be 1, there will not be any change in the static pressure, right. But if m 1 is greater than 1, then what happens to the pressure P 2 by P 1? It will be greater than 1, right, because if m 1 is greater than 1, this term will be positive or the greater than m 1 square. So, it will be positive, therefore, and it will be more than 1, this term P 2 by P 1 will be greater than 1, right. As it goes, these terms will be P 2 by P 1 will be goes on increasing. What it indicates? It indicates the downstream pressure will be higher than the upstream pressure, that means static pressure. Okay. All right. So, and if m 1 is tending towards infinity, that becomes P 2 divided by P 1 tending towards infinity. Similarly, we get expression of density and temperature ratios like rho 2 by rho 1 is equal to gamma plus 1 m 1 square divided by gamma minus 1 m 1 square plus 2. And in the similar way, it is a function of Mach number 1 and gamma, and when gamma m 1 is equal to 0. So, what will be that then? Means this term will be 0 and this also will be 0, right. It will be having certain values, whereas when m is greater than 1, this rho 2 by rho 1 will be greater than 1, right. Yes or no? If m 1 is greater than 1, right. So, when m 1 is tending towards infinity, rho 1 divided by rho 2 divided by rho 1 tending towards gamma plus 1 divided by gamma minus 1. So, similarly, we can have T 2 by T 1 in terms of Mach number and gamma. We can derive this expression by just putting these values over here, means I can take these values over here, basically these values over here, and this portion I can take over here and get this expression. And when m 1 is greater, than 1, T 2 by T 1 will be greater than 1, right, or less than 1. What it would be? If m 1 is greater than 1, right, it will be greater than 1, right. And if m 1 is going, tending towards infinity, T 2 1 by T 2 divided by T 1 will be tending towards infinity as well. So, let us look at one concept, which is very important. Whatever we have derived, these expressions will be valid even if the upstream Mach number is less than 1. Am I right? But is it physically possible or not? How we will determine? Because we have never told that Mach number cannot be less than 1, right, whether shock will be formed or not, right. We started with the equation, nowhere we have told that look Mach number cannot be 1, whatever the equation we have derived till now. Then we need to invoke the second law of thermodynamics to judge whether the normal shock or the shock will be formed or not. For that, we need to look at entropy across the shock, and that is S 2 minus S 1 is equal to C p ln T 2 by T 1 minus R ln P 2 by P 1. We will be using this expression, T 2 by T 1, that is equation 6 over here, and similarly we will substitute these values, P 2 by P 1 from equation 14. If I will substitute these values, I will get, if you recognize this term is nothing from here, and similarly these terms is from the upper one like here. Now, what is saying? It is saying that entropy change is a function of m1, that is inlet Mach number, and gamma, and if this according to the second law of thermodynamics, that is entropy always will be greater than equal to 0, that is the condition, right. It can never be less than 0, am I right? So, therefore, let us see that where it is being violated. If m 1 is equal to 1, then what will happen? S 2 minus S 1 is equal to 0. That means, entropy change is 0, which is possible. That means, which is corresponding to your Mach wave. And if m 1 is greater than 1, S 2 S 1, S 2 minus S 1, it became this term will be greater than 0. Yes or no? If I put it m 1 greater than, this term will be, this term in this zone, it will be larger. So, that and whereas this term also will be, and together it will be greater than 0. But if m 1 is less than 1, then entropy change across the shock wave will be less than 0, which is not really possible. Therefore, if Mach number, inlet Mach number is subsonic, then shock cannot be formed. So, normal shock cannot be formed, right. But question arises, why the entropy will be increasing across a shock when the inlet Mach number greater than 1? Why? What is the physical phenomena really occurring for entropy to increase across a knock? Why it is so? Irreversible, but how it is occurring? Why? I mean, what are the causes?
Rapid changing.
Yes, that means if you look at the shock is very thin, as I told 10 power to minus 7. So, the gradient of temperature, pressure, densities are quite high to cause a dissipation. Dissipation in case of what? Viscosity, I mean a conduction, and also the others, right. So, therefore, it is an irreversible process, right, across that, and entropy change occurs across the same. So, with this we will stop over, we will see in the next class.